I'm going to be talking about invariant theory for maximum likelihood estimations. There's some connections between groups and invariant theory and statistics. And this is all joint work with these wonderful collaborators, Carlos Améndola, Kathlén, Kohn, and Philipp Reichenbach, pictured here. All right, so I will start by describing the statistical setting that I'm going to be talking about. And it's given by this picture here. So we have some space, which is this red triangle as a cartoon for our space in which our statistical model lies. So that's this black curve inside the space. Okay, so this cartoon picture has some more concrete realizations, let's say. So we can think of the setting of a discrete random variable. So having finitely many states, let's say it has m states, then our probability mass function to give the information of this random variable is some tuple of m numbers. So that's our vector p, where the jth coordinate is the probability that the random variable takes the value j. So for example, this could be a weighted m-sided die. And in this case, a statistical model is given by a subset of the probability simplex. So our red triangle here represents the probability simplex, which is the set of all non-negative vectors with entries summing to 1. So this is a particular polytope that in the case where m is equal to 2, no, m is equal to 3, looks like a triangle. All right, so that's one statistical setting that we'll be looking at. Another is that of a multivariate Gaussian. So now we have a random vector in some, let's say, again, m-dimensional space. So now x has m real coordinates, and we have our probability density function, which takes this form. So this is the not quite standard form for the density of a multivariate Gaussian. It's not quite standard because I've written it in terms of the concentration matrix or the inverse of the covariance matrix. So this would usually be a sigma, and this would usually be a sigma inverse. Okay, and I'm assuming that the mean of this density is 0, and then a statistical model is just given by a subset of possible concentration matrices. So this is a subset of positive definite matrices. So in this multivariate Gaussian case, the statistical space we're working in is the space of all positive definite matrices, which yeah, I guess we also saw in some of the talks yesterday as well. And then a statistical model is just some subset of that space. Yeah, please feel free to stop me at any point if there are any questions. All right, so I said I was talking about connections between groups and statistics. So what about the groups part? Okay, well, first the definition. So a group is a set we'll call G of elements such that the identity is in this group. For every G and H in the group, their product is also in the group, and inverses of each element are also in the group. And we'll say that G acts linearly on some space V, which means that each group element gives us a linear transformation of the space. So this is easiest to see for an example. So we can start with the symmetric group. And it acts on some space via the permutation matrices. So for example, if I start with the symmetric group on 3 elements, then I can think of it as acting on R3, where the action is by these permutation matrices. So if my element of the symmetric group just swapped elements 1 and 2 and left 3 alone, then this is the permutation matrix that it would correspond to. And we can see that if we apply it to some vector in V, which in this case has 3 coordinates, it has the effect of swapping the first 2 coordinates and leaving the third coordinate alone. Okay, so some more group definitions. So an orbit is the set of all points you can reach, starting at some fixed V and acting by elements of the group. And invariants are functions that are constant on orbits. So let's go back to this example to see some invariants. Well, we can check that each of these polynomials will not change if we apply permutation matrices. So for example, we have this permutation matrix, and we can see that it hasn't done anything to the sum of the entries. We still have V1 plus V2 plus V3, or the sum of the pairwise products or the triple products. Okay, but in fact, something much stronger holds. So these polynomials, well, they're elementary symmetric polynomials, and they generate the ring of invariants. So given any function, any invariant, so a function that's constant on the orbits, it can be written by taking some combination, some products and sums of these invariants. Okay, so the connection between groups and statistics is not new. It is maybe first appears to us in the idea of what's called IID, so samples being independent and identically distributed, which is a very common assumption in statistics. And what this assumption means is that permuting our observations doesn't change anything. So the observations don't have a particular order to them. We can change the order. And it's saying that they're invariant under this group of permutation matrices. So that's one place where groups meet statistics, and there's others as well. For example, in these 3 papers, all from the Annals of Statistics. So there's this notion of group symmetry models, which look at covariance matrices which are invariant under some group. And there's also the notion of a transformation family, which is a statistical model in which a group acts transitively. Okay, so the message in this slide is that groups and statistics have existing connections between them. All right, so now I'll zoom in a bit more on the particular setting in statistics that I'll be talking about, and that's parameter estimation. So we have a statistical model. So that was this black curve here inside this red space. And then we have some data, which we can also view as a point in this space. So there's our data point here. And we want to use the data to estimate parameters in the model, which means to find the point on the model that's closest to the data in some appropriate sense. So in particular, maximum likelihood estimation finds the maximum likelihood estimate, which is the point in the model that maximizes the likelihood of observing the data. So then likelihood is a function which gives a measure of closeness between a particular point on the model and our data point. So we can compute our likelihood function everywhere along the model and find where it's maximized given our data. Okay, so I mentioned before these two settings of discrete and multivariate Gaussian. So what does maximum likelihood estimation look like in these cases? Well, okay, so discrete, we had our random variable with m states. Then our model was a particular set of probability mass functions inside the simplex. So just this curve here, and then our data is, I mean, we can imagine if we're rolling a weighted die and we wanted to collect data for it, what would we do? Well, we could write down everything that happened as we rolled the die various times, or we could summarize it by this vector u, which just records the fraction of times that each state j occurred after some number of rolls. So that gives our data point, which is then also a point in the probability simplex, because these fractions are non-negative and sum up to 1. Okay, so then the likelihood function, I guess if you take the unknown probabilities and raise them to the powers of these numbers, this gives the likelihood, and often it's more convenient to work with the log likelihood, which has this form: the sum over I of ui log pi, and then the MLE maximizes is the p in the model that maximizes the log likelihood. So that's the maximum likelihood estimate, or MLE, denoted by p hat. Okay, and for example, one possible model is to just say that everything is in the model. So the whole probability simplex, every possible tuple of non-negative numbers summing up to 1, they're all allowed. And then the unique MLE is just this data point that you started with. So that's our best estimate. But in practice, the models would be much smaller, and then the data point will usually not lie on the model, and we'll do some kind of projection, some kind of distance geometry. Okay, so what about in the multivariate Gaussian case? So now we have our random vector in Rm. The model is a set of possible positive definite matrices. So it's a subset of the positive definite Kohn. And the data in this case is, well, we take we generate some samples. So these are random vectors yi living in Rm. And we can summarize the data that we collect by the sample covariance matrix, which is this sum of outer products of the sample vectors, then averaged over the number of samples that we have. And this will give us some positive definite matrix, so some point in the positive definite Kohn. So that's our data point. And in this case, the log likelihood has this form. So hopefully you'll take my word for it, that it can be written as the logarithm of the determinant of psi minus the trace of psi times the sample covariance matrix Sy. So this is the function that we're looking to maximize. This is our notion of distance to the model. And then the maximum likelihood estimate is the possible psi in the model that maximizes this log likelihood. All right, so for example, we could let the model be the entire positive definite Kohn. And in that case, we can show that the unique maximum likelihood estimate is for psi, for the inverse covariance matrix, is just the inverse of the sample covariance matrix. All right, but there's a possible problem with this, which is that the MLE then doesn't exist if this matrix cannot be inverted. So the sample covariance matrix is a M by M positive semi-definite matrix, but unless it has rank M, its inverse doesn't exist, and then the maximum likelihood estimate doesn't exist. So that gives rise to the idea of a maximum likelihood threshold, which is a number that tells us how many samples do we need for various good things to happen when trying to compute our MLE. So we can ask, okay, the worst case scenario is that the log likelihood is not even bounded from above. So we can ask how many samples do we need for our log likelihood to be bounded. And then even better, we could hope that it attains its bound, and then a maximizer is the MLE. So we can ask how many samples are needed for the MLE to exist. And then even better, we could hope that the MLE is also unique and that we can guarantee that by having enough samples. Okay, and this was studied, for example, in this paper on the existence of maximum likelihood estimators from the 90s. So to go back to our example, we had our model, which was the whole positive definite cone. The unique MLE was the inverse of the sample covariance matrix. Then in this case, thresholds 1, 2, and 3 are all M. So as soon as we have M samples, then generically this matrix will have rank M, because we're summing up, it's an M by M matrix, and we're summing up M rank 1 matrices. And so all three of these good properties happen all at once when we get to this threshold M. But if fewer than M samples, then the log likelihood is not even bounded. Okay, so that's what I said. If we have at least M samples, the MLE generically exists and is unique. But if we have fewer than M samples, then it's unbounded. Okay, but this is a lot of samples to require because M can often be quite large. But smaller models usually need fewer samples. And for example, if your statistical model is a graphical model, so given in terms of a graph, then you can describe these thresholds in terms of the graph structure, as studied in this paper of Ulla. And recently, I recently learned of some connections between this problem and rigidity theory, which is one of the themes here. So I thought I'd mention that. And there was a talk by Daniel Bernstein in an earlier mini symposium at the program discussing these connections. Okay, and now back to the groups side. We had this group G that was acting linearly on our space V, and we saw that the orbit was the set of points that we could reach starting at some V. So here's a picture of the group setup. We have some V here, and we act on it via our group. So let's imagine that the orbit that we get is this curve here. And then we define the capacity to be the smallest distance of the orbit to the origin. So it's the infimum as we range over elements in the group of the norm of G dot V. So in this picture, the capacity is this distance here, or maybe this distance here squared. Okay, and then we can make various definitions. So we say that a point V is unstable if this capacity is 0. So this means that this distance here is 0. So the origin is not necessarily in the orbit itself, but in the closure of the orbit. And the set of unstable points is called the null cone, and it's a very classical object of interest in invariant theory, dating back to Hilbert, and it's the set of all points where all invariants vanish. Okay, so then the opposite of unstable is semi-stable. So a point is semi-stable if the capacity is strictly positive. And then we have two even stronger notions than semi-stable, which are increasingly strong. So a point is called polystable if it's non-zero and the orbit is closed. And you can check why this implies that the capacity is strictly positive. And even better, it's stable if not only is it polystable, but the stabilizer is finite. So the stabilizer is the set of group elements that leave the point fixed. All right, so before I was describing this permutation matrices arising from the symmetric group. So what happens in some space, and we act on it by a finite group, then so we have these four definitions, these four possible notions of stability that can hold at a particular point, and they depend on our group action. So for example, we can consider a finite group, then we have some point in our space and the group moves it around to other points. So what can happen? Well, can we be unstable? So can our point get sent to 0? Well, only if it started at 0. So once you get to 0, you can't escape by multiplying by matrix. So we see that the unstable point is the origin itself, and also we can see that any other orbit is going to be closed. So any other non-zero orbit is closed because it's just a finite union of points. And also every stabilizer is finite because a stabilizer is a subgroup of the group and the overall group is finite. So the stabilizer is also finite. So in a finite group, we're either unstable or we're stable. And that's a very nice situation to be in from the point of view of looking at invariance and invariant theory. But for other groups, we have these notions of semi-stability and polystability that interpolate between these two extremes. So here are two other examples in case you'd like to try them out and haven't seen these stability definitions before. So we can consider GLM, the group of all m by m invertible matrices, acting on Cm by left multiplication. And okay, as a then slightly more difficult example, we can consider the product of special linear groups as SLM1 by SLM2 acting on rectangular matrices, and ask which of these stability notions can arise here as we vary our rectangular matrix. Okay, so this is the main slide of the talk. So in case you want to listen to the talk, but only to one slide, this is the slide. How is invariant theory and maximum likelihood estimation connected. And this is the topic of two recent papers with my co-authors who I mentioned. So we have our two settings that we're looking at. We have this setting of invariant theory with a point and then its orbit, and looking at the closest distance of the orbit to the origin. And then we have this statistics picture where we have our space and our statistical model inside that space, and then a data point also in the space, and we're looking for its maximum likelihood estimate for the point on the model that best explains the data. Okay, and essentially what we show in these papers is an equivalence between these four notions of stability that I described for a group action, so unstable, semi-stable, polystable, and stable, and these four sort of increasingly good things that can happen to the likelihood function when you try to maximize the likelihood in a statistical setting. Okay, so this correspondence requires certain assumptions, both on the invariant theory setting and on the statistical setting. I don't know how it would make sense for it to hold just in general, but I'll now describe the types of groups and the types of statistical models for which this correspondence holds, and some of the proof techniques in building the correspondence. Okay, so the first setting is where we have a torus action described by some matrix. And then, so that's on the invariant theory side. And on the statistics side, we have a log linear model. Okay, so for such a setting, which I'll go into a bit more detail shortly, this is what the correspondence looks like between our notions of stability and our properties of the likelihood function. So firstly, the unstable and stable cases don't happen. But then the semi-stable versus polystable distinction tells us when our maximum likelihood estimate exists. And if it doesn't exist, there's an extended notion of maximum likelihood estimate that we can use instead. So testing the polystability of a point tells us when this optimization problem has a solution. Okay, and here is, I guess, the terms and conditions of this correspondence. So all the extra ingredients that are required to build this correspondence. So maybe I won't go into too much detail about these, but feel free to ask if you're interested. So basically, we need to build the group action that corresponds to the model in such a way that the correspondence holds. And then the proof idea is that there are polyhedral conditions for maximum likelihood estimate existence. For instance, they can be found in this paper here by Erickson, Feinberg, Ronaldo, and Sullivan. And these conditions can be related to the Hilbert-Mumford criterion from invariant theory. Okay, so what even is a log linear model? It's a set of distributions whose logarithm lies in some fixed linear space. So this can be written in as a set like this. We have our vectors P of probabilities whose logarithm lies in the span of some particular matrix. And they include many examples as special cases. So the independence model or graphical models or hierarchical models are all log linear models for a particular choice of matrix A. For example, we can let A be this 6x9 matrix here of zeros and ones. Okay, and then what does it mean for the logarithm of some probability vector to be in the row span of this matrix? Well, it means that the log of Pij is lambda I plus mu j, where lambdas and mu's are some general linear combination of rows that we took. And this is the independence model. If we exponentiate, we then have that Pij is the product of something that depends only on I and something that depends only on j. So that's how the independence model arises as a log linear model. And you can do something similar to build graphical models and so on. Okay, and why would we expect that these might be related to torus actions? Well, the log linear model can be parameterized like this. So we start with some vector of a d-dimensional positive vector, and we apply this this map, which up to normalization constant to make sure all the entries sum to 1 is a monomial map. So its jth entry is what I've denoted by theta to the aj. So it's this product of theta 1 to the a1j dot theta d to the a dj. And this is closely related to what we get under a torus action. So we can consider the group of complex diagonal invertible d by d matrices. So just non-zero complex numbers on the diagonal. And then a matrix gives us a group action by multiplying by matrices whose diagonal entries look like this. So they're the same as these products, these monomials that we saw here. Okay, and I won't worry about that, but this gives an idea for how the torus action is related to the log linear model, and that we might expect some sort of similarity between the properties of the group and the properties of the model. Okay, and I'll conclude by talking about the multivariate Gaussian aspect of this correspondence. So here, the models that we look at, we call Gaussian group models, and you get them from groups as follows. So you have some group of m by m real matrices. Then the Gaussian group model is, okay, it has to be a set of positive definite matrices. So we want to build some positive definite matrices from our real matrices. So we can take G transpose G, where G lies in the group. So that's our model. And so then in this case, we can start really with any group or any group that acts linearly on Rm. And it gives us a corresponding Gaussian group model. And in this case, our correspondence between stability notions and properties of the likelihood looks like this. So our point is unstable if and only if the likelihood is unbounded from above. It's semi-stable if and only if it's bounded from above. It's polystable if and only if the MLE exists. And stability implies that the MLE is unique, but not conversely. So we've almost got this full correspondence between the 4 properties on the invariant theory side and the 4 properties on the statistics side. Okay, and the stability is not under the whole group, but under the matrices in the group of determinant 1. Okay, and here we started with a group of real matrices, but if we started with a group of complex matrices, then in fact we get equivalence of all 4 conditions. Okay, and just for an idea of the proof, so I told you before that this is the log likelihood function, log dep psi minus the trace of psi sy. And the idea is that if our group looks like this, so if each concentration matrix in the group has this form G transpose G, then just substituting in that expression means that we can write it like this. So we have this part involving the determinant of G transpose G, and then something that we're subtracting off that is the norm of G acting on Y. So that's our capacity that we saw before. So hopefully that gives an indication of why we can expect these two settings to be related. And I'll skip this slide and just say thanks a lot.
Thank you for the very interesting talk, Anna. Are there any questions?
A quick question.
Yes.
Hi, Anna. On the previous slide, so where you don't have the converse, is that just a statement you haven't proved, or do you have a counterexample where it's actually not stable?
Yeah, we have a counterexample. So in the, so you really need structure, some compactness structure you get in the complex case, but not the real case. So yeah, so this converse doesn't hold here in the real case. It's sort of interesting because for particular groups of interest, you can come up with other characterizations of stability, like unstable, semi-stable, and so on, in terms of sometimes in terms of vector spaces and all this kind of thing. And there's sort of another notion of stability that's not the group stability, but something else. And in certain cases, that is equivalent to there being a unique MLE. So it's, that bit's sort of still not quite worked out.
Cool, thank you.
Thanks.
Are there any other questions?
I'll ask one.
Hi.
Hi. Thanks for the great talk. I was curious about for what groups on this slide, even like how hard it is to compute the MLE if it exists in those cases. Like what sorts of groups can you actually like compute the thing for?
Yeah. That's a good question. So there are particular models of interest which correspond to particular groups of interest, and one that has, I guess, seen a lot of attention recently is where the group action is a product of special linear matrices, and then the corresponding statistical model is called a matrix normal model or a tensor normal model. And there it's, I'd say, the complexity of finding the MLE for in those cases is the question of complexity of matrix scaling or tensor scaling. And like there's work by, I don't know, Bergesser et al. To develop like polynomial algorithms to, well, they're interested in testing if a point is unstable or not, but the algorithms can also be used to converge to a particular point, which if the MLE exists will be that point. So for some groups, I guess it's easy, for some it's a topic of interest to understand the optimization problem and its complexity and so on. And for general groups, it's very difficult and not much is known.